right, wake up. I'm going to involve a little more class participation than usual because I don't want to talk for 90 slides, but that's what we're going to get through today. I know. How many people are excited about learning about theropods? That's what we came for, right? That's honestly, it is, right? I'm humbled to be able to present on theropods because, that's what made me, as a child, they were just wonderful. I was a kid that was very, very moved by Jurassic Park, like so many of you probably were. So theropods are near and dear to me, and I'm a herpetologist by trade, but I've always had a passion for dinosaurs. So this is going to cover a lot of chapters. It's going to follow your book, mostly. We'll talk about that when it deviates. And there's going to be some other stuff in there. So we're going to talk about theropods, general characteristics. Then we're going to talk about systematics. It'll get a little slow. Bear with me. And then we're going to go into bird evolution, or lack thereof. You'll decide. So we're going to cover a lot. Feel free to take a bathroom break. Put your head down. It doesn't matter to me. I have thick skin, like theropods. All right, before we get started, what did we talk about last night? What did Dr. Chadwick address? Sauropods. So where are we at on here? So Saurischia, right? So we're covering Saurischians. That's what we started with. We haven't gotten to ornithischians yet. All right, so theropods are going to fall under Saurischians. What was the difference between Saurischians and ornithischians? Their hip. What about their hips? What bone is this? The red? Ilium. The one that's anterior, close to the head? Pubis. The one posterior? Ischium. So a Saurischian, these are separated, right? Pubis and ischium are separated. For ornithischians, what? They run together, almost in parallel. So we're going to stick with these that have these separated bones. Just another picture. I like to give my students lots and lots of pictures. If you want this lecture, I do. If you want this lecture, you can ask me and I can load it on your computer. But the more diagrams you have, maybe something looks better to you on a different picture than another one. So I give you lots of different resources. So same thing. We're going to be talking about these big guys, and we'll get to these soon. All right, this is important. I assume this may be on your exam, one of the most important things. Shared characteristics of theropods. All right, I'm wandering. So I like to walk. This is tricky because any resource you look at, different textbooks, different online resources, different opinions, they'll give you different characteristics of what, generally explains what a theropod is. These are the ones that I find important. There may be others that are not on here, but I find these most significant. Obligatory bipeds, what does that mean? They have to walk on two legs. So we're not walking on four legs anymore. And to back up, theropod, therobeast, pod foot, literally beast foot. Pneumatic bones, what does that mean? Hollow, so we have hollowing of the bones. That's really different than the sauropods and things like duck-billed dinosaurs, which we'll get to soon. Enlarged manus, what's the manus? The hand, okay, so we're going to bust out some scientific terms now. So upward of 50% of the length of the rest of the forelimb, so big hands. Why have big hands? Grab, right? They're using them now. They're not just using them to walk, they're using them to, a lot of times, to consume prey. All right, reduction of the fourth and fifth digits of the manus. So we're going to see a loss, or just an absence, I should say, of some of the fingers. Compact, elongate, narrow pes. What's the pes? The foot, and then once again, digits 1 and 5 reduced or absent. And they're digitigrade. Do you know what digitigrade means? Walked on toes, so they were up off the balls of their feet, which is also different than sauropods. So if you see tracks, a lot of times you're going to see toe prints. Zyphodonts. A zyphodont is something that possesses sharp teeth, often serrated. Now this is typical of most theropods, but not all. Right? Not all theropods had teeth that were sharp or serrated. Some didn't have teeth at all, but generally they did. And then most of them had claws present on all digits, hands and feet. Now the claws might have been different shapes, but they were present. Slow me down if I go too fast, because we do go through a lot. All right, any questions? All right, so just to look at some of these characteristics, you can see the front foot, pretty much just those 3 toes, those 3 digits. Hind foot, 3 prominent, 1 reduced, 1 just not there. Much different than the sauropods. We won't talk about the femur, claws present, and then we'll get to all these extra holes in the skull, especially this extra fenestra later in the lecture, but that's not characteristic of all theropods. Yes?
What is the use of this digit?
A lot of scientists consider it to be a vestigial digit of no use. So that's the honest answer, of no use. Okay, so I like to illustrate as much as I can. If I can't find a picture, trust me, I looked hard. I like pictures, yes.
So are all theropods carnivores?
No, they're not. Most are, the large majority are, but not all of them. So we'll get to some of the ones that might have consumed other things. So who were the theropods? You all know this. You spent your life watching movies. T-Rex, where's he famous from? Jurassic Park, of course. Spinosaurus was made famous in Jurassic Park 3. You're going to hear lots of Jurassic Park references. Gallimimus, Jurassic Park. The big raptor, right? Utah raptor. Not Velociraptor. Utah raptor was the big one that you've seen in a lot of movies. And then a funny little comic. Of course, everyone makes fun of T-Rex and his short little arms. Even though he was quite studly, those arms were strong. Short but strong. Kind of like me. All right, theropod paleobiology. This is something a lot of people will skip over. I won't, because I like this stuff. I like to pretend or like to think about what did the dinosaurs do? Not just let's look at the bones and relationships. So pretty much you can sum up their life by tracked, attacked, and fed. Just the craziest carnivores this earth has ever seen. All right, how big were they? Were they all huge? No, right? We think about T-Rex and some of the other big theropods, but they really weren't all that big. So non-avian theropods range in size from less than a meter to upwards of 15 meters when you get to T-Rex, Spinosaurus, some of the others. But the most of them were smaller. Things like Compsognathus, things like the Microraptor. Little bitty guys, about the size of a sheep or a house cat. All right? How were they able to reach these immense sizes? I love to think about these hypotheses. All right, this goes beyond just the bone bed. This goes into ecology, which I love. How did they get so big? What does it take to get big? Food, right? So where would all this food come from? The environment would probably be pretty productive, right? They probably had a pretty healthy environment back in those days, unlike the tainted environments we have today where we really don't see too many pristine environments. So there's probably lots of food. Lots of food resources mean you can support lots of grazers. So hadrosaur, ceratopsids, big herds of animals. I think that's why we're finding huge herds of duck-billed dinosaurs, right? They were grazers, and if you study ecology, grazers will have higher biomass, greater numbers, because there's more plant matter available than the predators. Right? Could they survive today? No. If you think about wolves, bears, lions, they're having problems today because they don't have a large enough territory, not enough food resources. So there's no way these big animals could survive today. But in a productive ecosystem with lots of hadrosaur herds, yeah, they probably did great and got very large. How fast were they? So all this, how big they were, how fast they were, this all goes to how were they as being a predator? How efficient were they? So troodontids, which we've been finding out here, right, and ornithomimosaurs were probably the fastest. Ornithomimosaurs were kind of like an ostrich. Hypotheses will predict that they may have been from 25 to 40 miles per hour in top speed. That's pretty fast. That's faster than me. It doesn't take much to be faster than me. But that's about the speed of a tiger, all right? So how do they get those estimations? Well, muscle mass that could have been on the bone that's present, hind limb proportions. You can go out and you can study how fast a cheetah runs and then look at the biomechanics of that animal. So we can use what we use today to estimate speed and look at the efficiency of animals, to look at the bones of dinosaurs. So these estimations are pretty accurate. But it's a little harder with the larger theropods just because they were so big. The most conservative and probably the most accurate estimates say that T-Rex probably walked slower than humans. All right. This was an immense animal, just huge. Estimating running speeds have been anywhere from 5 to 45 miles per hour. I don't know who put the 45 miles per hour out there in the literature, but they did. There's probably no way, because recent studies that have done modeling based on the proportions of the animal say that the amount of muscle he would need to get to that speed would shatter his bones. It's just such a big animal that there couldn't be enough muscle to reach those speeds. Realistically, he probably ran about, or she, ran about 5 miles per hour. So, but
Easily outrunnable? Supposedly.
depends. You just have to outrun the slowest person in your group. So we have a range of speeds. All right, the cool stuff, weaponry. Some of these dinosaurs were loaded, right? And we can get into skulls and teeth all day, but what else? Dromaeosaurids. What are the dromaeosaurs? The raptors, right? Well, that's kind of what the famous representation of that group is. And troodontids usually had these enlarged claws on the second digit of the pes. So you can see these big claws, once again made famous in movies, that were probably used for subduing prey. If you got caught by this in the stomach, it would hurt. It would disembowel you. But recent studies have said that they may have not been that efficient at slicing and dicing prey. What this also would probably be useful for is climbing. So an anchor for climbing. So not only could this be used for subduing prey, but also for scaling trees. Not only did they have big claws, they also had powerful hands. Many of them look like this, with large arms, large hands, and that would be an effective way of taking down prey. All right, how bad were the raptors? We see them in the movies. But is what we see in the movies, is that true? I don't know, let's talk. Not necessarily, right? They probably were extremely agile, just like they've been portrayed in the Jurassic Park movies. If you look at the skeletal system and the biomechanics, they're extremely balanced. They have a horizontal position vertebral column, so it goes straight across like this, and then that would be balanced on top of legs. They create a center of gravity near the hips. So what that means, it means they were balanced. And when you're balanced, you can be agile, you can be quick. They also had a stiff tail that pivoted posteriorly to the pelvic girdle, so it had a pivot point here, back and forth, and they also had interlocking caudal vertebrae. So the vertebrae actually locked together, more so than a lot of animals, and made it rigid. It's almost kind of like a rudder. So you have this perfect, locked-in, balanced animal. On top of that, their bones were what? Hollow. So they're lightweight, and they have powerful skeletons. So even though they're hollow, the way they're put together makes them powerful and fast. If we look at biomechanics, they have efficient systems. So yes, if you look at the skeletons, they probably were really fast. They could jump high and take down prey easily. Jaws and teeth. In almost every class I teach, especially comparative vertebrate anatomy, we look at skull morphology. That can tell us a whole lot of things about an animal. Theropods, did they have molars? Probably not. We really don't find molars in theropods. Take out molars, can they chew? Not really. So they probably didn't chew. What they did do was they used their teeth to subdue prey, grasp onto them, and then dismember that prey, rip it apart. So they probably used a slash and tear technique similar to how crocodiles feed. Crocodiles don't chew up their prey slowly. They grab it until it dies, and then they rip it apart. So if we look at the skulls of dinosaurs, they're most similar to the skulls of crocodiles. Types of teeth. We really can boil down the types of teeth to two categories. Thinner teeth with pointed serrations. So have you found a teeth that's very small, thin with serrations in the quarries? I know Ivan has. What is it? Troodons, right? So what do you think that was good for?
Slicing meat.
Yeah, that's probably really good at slicing, cutting off meat, right? Who had big, broad teeth with pretty small serrations? T-Rex. So I don't know if anyone's found a T-Rex tooth this year, but they were really shaped like a knife. They were really conical, almost like a crocodile. So that's probably great for grasping onto prey and then just crushing it. All right, they had an extremely powerful bite force, kind of like a crocodile. So they probably fed in similar fashion to the way a crocodile does. And if you actually look at the poop coprolites of T-Rex, you find bone fragments, which indicates that, yeah, they could probably crush bone. So here's a great example of kind of the two extremes of teeth. Troodontodon, you're going to see extreme serrations, just like a knife for cutting. Tyrannosaurus, big conical teeth for grasping and crushing. They say you don't feel the tearing of your skin when a crocodile bites you. You feel the crushing of your bones. You can put that in your notes. So a T-Rex, you probably didn't feel anything. All right. Toothless theropods. We did have a few toothless animals. So they lack teeth, but they had a cornified skin layer, most likely, similar to a duck. So even though they lack teeth, they did have some rigidity in the jaw. So what would that be good for? Is that good for tearing and slicing meat? No, right? So we know they go in the theropod group based on their skeletal anatomy. But like I said, not all theropods ate meat, so they probably fed in aqueous environments, maybe grind plant matter up, look for crustaceans, invertebrates, sift through the soil. Very similar in a way that ducks do it. If you see ducks kind of dabbling through the soil. Oviraptors, so that would be something like one of the mimosaurs, Gallimimus, whatever it may be, probably did something like that. They had long jaws. They probably weren't especially effective at crushing. Yes?
The Oviraptor is one on top, the other one is the Mimosaur.
I'm sorry?
You pointed to the wrong one.
Oviraptor right here.
Yeah.
Yeah. Okay. So oviraptors had shorter boxed jaws. So the pressure was in a smaller area, so they were probably better at crushing things. So they probably crushed animals like bivalves, shells, right? So you have that type of jaw, you're not ripping apart meat, you're crushing something. Maybe you haven't had ecology yet, but when you have all these different jaw types, that's great at maybe niche partitioning. What is that?
It means that the animals, they have their role in the ecosystem. They eat certain food, they prey on certain animals, they interact with certain things,
Yeah.
so that it has more space for other animals to do.
So we have to limit competition, right? So when you have different jaws, different head sizes, you feed on different food items, you can limit competition on that one limited resource. So yeah, I like to study dinosaurs in the same way we study ecosystems today. All right, what else? Senses, olfaction. In Jurassic Park, they're like, don't move, right? You can't see me. All right, they weren't worried about smell. Do you think they could smell?
Sure.
Well, how could we tell?
They're narrow opening.
Narrow openings?
And brain endocast?
Yeah, we can look at the brain, cast the inside of the skull, look at the brain, and we know generally where the olfactory bulb is, the part responsible for smell. So if we look at animals today, something like a shark, this front part is the olfactory bulb. It's quite large, right? And we know that sharks are great at smelling their prey. So this is the inside of a T-Rex brain. No joke, you're looking at a T-Rex brain. The olfactory bulb is not small. It's quite prominent. So that's a pretty good piece of evidence that tells us T-Rex could probably smell. So the movie's not right in that point. Optic, could they see? If you look at the orbit of a dinosaur, what goes in the orbit of the skull? The eyes. Were the orbits small? No, not at all. So you look at animals today, burrowing animals, they have very small orbits or none at all. Dinosaurs, a lot of them, especially theropods, had huge orbits, which means they probably had very large eyes. When you have large eyes, you probably use them, so they could probably see quite well. Dromaeosaurids and troodontids had forward-looking eyes, something like this. So that means that their fields of vision probably overlapped, something like an eagle or us. That means you have stereoscopic vision. So they could also probably perceive depth. So they probably had great vision, to be honest. The theropods were just, like I said, I'll just keep talking about it. They were adapted for killing. All right, auditory. What is auditory? Hearing. You think they could hear? Yes. They had openings, so they could probably hear. But let's go beyond that. A really interesting study that your book brings up, a case study, and I like to test on case studies. I don't know what Dr. Chadwick does, but work done by L.M. Whitmer. He found that the two ears communicate with each other by a hollow channel. He called it the interaural pathway that passes through the brain case. So that's saying the ears are connected. All right, sound waves can go between them. So each ear transmits the same sound wave. They pick it up, it goes to that same little tube, and they transmit that to the inner ear, but they do so out of sync. One's going to do it faster than the other, right? If the frequency is coming in from the direction of where the sound is being produced, correct? So what is that going to do to you when you have out of sync hearing? What does that mean for sound perception?
Not that good. It kind of overlaps, so you can hear something twice.
What about if you can distinguish which way sound is coming from?
I think the opposite. You can extinguish it, know exactly
Yeah.
where it is.
You can zero in on where that sound's coming from. So they probably heard a break of a twig, and they knew exactly it's coming from over here, because those frequencies went through that canal and reached the inner ear on one side faster than the other. So really cool. So not only could they see and smell, they could also hear extremely well. So this is actually, I couldn't find a picture of that anywhere. I even tried to find his original paper. But if you go back and look at the brain of another dinosaur, this is a type of duck-billed dinosaur. Here's the inner ear. All right. So the inner ear is quite large. It's developed like it would be in mammals today. So that tells us they could hear. Also, it would tell us something about equilibrium. I'm sorry, Nigersaur is a sauropod. All right, dinosaur stomach analysis. I've done lots of stomach analyses, never on a dinosaur. How do you do this? Coprolites, or what you find in the stomach, fossilized. So just a quick list of what they found. They found young, indicating cannibalism, lizards, mammals, fish, obviously hadrosaurs, protoceratops. So we actually have this famous fossil here of a raptor fighting with a protoceratops, indicating that he's probably preying on this animal. So if you look at all the diet items found in the stomachs, and you look at predators today, theropods were probably dietary generalists. Whatever they could find and kill. They probably didn't specialize. How did they subdue their prey? We can only guess at this, but there's a few different hypotheses. What would this be? Teamwork. This would be like a group attack, right?
Ambush.
Yeah. So an ambush from several different individuals. They thought raptors did this. What would this be?
Like a brute force attack?
Yeah, like solitary pursuit. So one animal with a big head and lots of teeth went at the dinosaur, took it down himself. What about this? This is, yeah, it's ambush, right? Stalk, ambush, lie in wait. I'm sure some of the dinosaurs did this, but we're not for sure. There's actually some evidence that T-Rex might have had pockets for bacteria, kind of like a Komodo dragon did, above their teeth. And then some probably just scavenged. Social behavior. You think dinosaurs hung out with each other?
Depends on the dinosaur.
Some, maybe. So we see these ornate crests. We see these rostral protuberances like this on the front of the nose. What do you think those were for? What would be the function of this?
It creates a chamber. You can create like a very specific sound.
So resonance could be one.
Hierarchy system.
Yeah, also displaying information on other individuals. So let's look at modern animals. Rostral protuberances on a green iguana. It's used for mating. Right? The bigger the males have the larger protuberances on their nose. So dinosaurs probably use the same thing. Displayed health. The bigger males may have had larger crests. Defend territories, attract mates. We don't really know, but we can only guess based on what we see today. And then like she just said, They were most likely capable of making noises because if you look at the skulls, there's lots of open spaces inside that were probably really effective at being vocal resonators. So obviously that was made famous in Jurassic Park 3 when he blew into the raptor. I guess that was the inside the skull that they made with the 3D printer. And then social behavior continued, offspring care. They have found they found several nests now of oviraptors sitting on the eggs. So they probably at least incubated their eggs. We don't know if they took care of their young after that, but they made it that far. All right, that was fast. So that's just some general characteristics and just making up some cool things about the way we thought dinosaurs lived. So systematics. Now we're going to talk about the different classifications of dinosaurs. We're really going to talk about the major groups and clades. We'll mention a few species, but we're not going to go that deep because we don't have that much time. Ooh, it's kind of cut off. So we already studied sauropods. So we're just going to go all the way down this list. And over here are some of the major groupings. So we looked at sauropods. Now we're looking at saurischians. So we're going to look at theropods. And we're going to start right in here with Ceratosauria. All right, Ceratosauria. Mainstream scientists consider these the primitive theropods just because they're usually found lower down, so middle Triassic to upper Cretaceous if we're looking at where they're found in the fossil record. A few unique characteristics. Sacral ribs fused to the ilia. So that means this area in here was probably fused together, and that just reinforced the pelvic girdle, usually for running. Pubic shaft axis bowing cranially. So this is Dilophosaurus. So look at that. Look how it's bowed up and towards the head. So that's really unique to this group. And fusion of the ankle bones, which I really can't show you. So Ceratosauria can be divided into three groups: Coelophysoidae, Ceratosauridae, and Abelosauridae. So we'll start with Coelophysoidae. What's the famous dinosaur in this group? Dilophosaurus. Did he have frills and spit venom? No, probably not. They got that from spitting cobras and the frilled lizards in Australia, but still a cool idea. They're probably relatively small. Skulls are narrow, not too boxy. So they had kind of slender skulls, and a characteristic that's unique to these guys, like Dilophosaurus, is a kink in the skull. At first, they weren't sure what that's for. Then they decided, well, maybe it was effective in catching fish. Just a little extra surface area for grabbing onto fish. And something else that lives today that eats fish, alligators and crocodiles. And do they have a kink? Yes, of course they eat other animals, but they also eat fish. Found in the upper Triassic to the lower Jurassic. And I'm going to go through this fast because it can get kind of boring. So stop me if you have questions. So the best known taxa, Coelophysis and Dilophosaurus. All right, Coelophysis, you can see it's a small animal, slender, long skull, kind of similar to what you would see like a Compsognathus, but a different animal. All right, Ceratosauridae. There's only one real member, that's Ceratosaurus. Crazy looking animal, right? T-Rex was cool, but this thing was really cool. You can see all the prominent ridges and protuberances coming off the top of the head. Also, this is kind of an artist's rendering, but it was kind of based on the vertebrae that they may have these projections like an iguana might have. All right, Abelosauridae, two families within this, Abelosauridae. So when you see Abelosauridae, that's one thing, and then families is Abelosauridae, EA instead. The other would be the Nosauridae. So if we look at Abelosauridae, the representative would be Carnotaurus, also with these big protuberances coming out over the eyes. And then this is a hard one, Messiacosaurus was this Nosauridae. And if you look at the jaw, it had really interesting teeth. They're not really sure what that's for. This is a smaller dinosaur, probably small mammals, maybe even fish. Once again, when you see extra surface area like that, it's usually for catching quick, small prey items. Right? Just another look at Carnotaurus. Some of these bony outgrowths, very blunt snout. And something I find really interesting, look at these arms. Everyone makes fun of T-Rex, but this guy or gal actually had the shortest arms. All right, that's fine. Maybe didn't need them. Maybe it helped with balance. But look at the pectoral girdle. It's not reduced like the arms. It's quite large. So scientists really haven't figured out why the pectoral girdle was so robust, but the arms were so small. And then a really boxy skull. All right, moving on. So we're going to start looking at Spinosaurus and Megalosauridae. All right, and now we moved in to Tetanuri. So we're moving into another major group. So this is in your book. It's displayed in a different way. If you have questions, you can come talk to me. The taxonomy can get a little bit confusing. So it means stiff tails. They had interlocking vertebrae because the zygopophyses overlapped. So you might hear Dr. Chadwick or me mention zygopophysis in the field. This isn't dinosaur vertebrae, but this would be the parts we're talking about. These little projections, and that's how the vertebrae articulated together, how they connected together. And then the other processes were for connecting to the ribs. All right, so these, this isn't a picture, but they would overlap greatly and lock together. Characteristics, 3 usable digits or even less. Prominent muscular ridge on the scapula. Anytime you see a prominent ridge on a bone, a lot of time that's for muscle attachment. And there's a lot of diversity in this group. This is a huge group. So first, we're going to look at Megalosauridae. So 2 families, Megalosauridae and Spinosauridae. Not much is known about Eustrepospondylis, but Spinosaurus is quite popular. But Megalosauridae, Middle Jurassic to Lower Cretaceous, includes Megalosaurus, Eustrepospondylis, and Afrovenator. Really cool name. So kind of a small dinosaur, similar in appearance to a lot of the theropods. Nothing really stands out about this animal. And once again, if I go fast, you can have this lecture, so don't worry about losing something. Megalosaurus is kind of interesting, though. It's from England, found in the Middle Jurassic. And this was the first dinosaur named. So it happened a long time ago. And look at the artist's renditions of this animal. So here it was before. And they found this animal a long time ago, even before they named it. And then it went to this, and it actually morphed into this. So paleontology is often a guessing game. And it's known from pretty poor remains. This is really everything that's been found. All right, Spinosauridae. I'm not sure why my bullets are different right there. What's really famous about these guys? The big sails, right? They didn't all have that, but the big famous dinosaur, Spinosaurus, had it. So it kind of represents the group. Had a nicely developed muscular shoulder region. So the arms were quite large with a large pectoral girdle. So they had strong arms and a well-developed elbow. You see how big the arm is? How long it hangs down? Really long snout, and it's named after Spinosaurus. And the original dinosaur that was found that described this taxa was lost in World War II. But this includes 3 main characters. There's one other, but Baryonyx, Suchomimus, and Spinosaurus. Baryonyx is from England, found in the Lower Cretaceous. He stands out that he's different because the neural spines are reduced. He doesn't have that large sail that Spinosaurus has. It's also just a smaller dinosaur in size. Suchomimus, you can see it falls in right here. So you see a little bit larger sail, but we're not yet to the Spinosaurus in size. And then Irritator, Challengerii, is the one we haven't mentioned. It would be the smallest. And then Spinosaurus is the most well-known, found in the Upper Cretaceous. Had a big sail, long limbs, long forelimbs, very powerful, long snout. So they really think this animal's aquatic. What other animal today has a really long, thin snout with a skull kind of like that lives in the water? Specifically, gharials, right? So it probably fed kind of like a gharial. When you have all that long snout that's narrow, that's not really good for holding on to a large prey item. probably fed on large fish. It's really good for moving through the water very quickly, very little resistance, and lots of surface area for grabbing onto prey. All right, yes?
Why would he need to sail in the water?
The sail has been widely debated with a lot of dinosaurs, like Dimetrodon. Why have this big sail? One of the, I guess, the best hypotheses that I've heard, and that's widely accepted, is thermal regulation. A lot of surface area for exchanging heat with the environment.
But wouldn't that cause drag on the water, like for the sailfish, where they put it back?
I don't think this animal's worried about speed in the water, though, like a fish, to be honest. So yeah, it'd probably create a little drag. But if you look at the animal, it's not shaped like a fish or a crocodile. It's not. I don't think this animal lived exclusively in water. It probably went back and forth. A monitor lizard is probably a good example, like a Nile monitor. All right, moving on. So now, Carniosauria, I've kind of put it right here on this. And Carniosauria, really the only representative group to this part of the curve that branches off of the Allosaurs, and then we'll go into the Coelophysis. So we're going to be looking at both of these underneath Carnosauria. And both of these also fall under Aviatheropoda. So you see Aviatheropoda is right here, then the Carnosaurs, and then Allosaurs, and then Coelophysis, and it'll go from there. All right, so these are the bird theropods. We're starting to look bird-like. Share characteristics, extremely complex air sac chambers in the vertebrae. So more hollowing of the bones. Lightweight, but still rigid enough to be of use. Promaxillary fenestra, so an extra fenestral opening in the skull. This picture, I just noticed, actually doesn't show it. But it would be right here in the bottom, and I'll show you on one of the next slides. Yes?
That's a Theropod.
Yes, it's not the right picture, thank you. Loss of the manual digit, 4, and then large nares. So we're going to see those two clades I mentioned, Carnosauria and Coelophysis. And look at the nares. Well, this isn't the animal, but it's kind of representative of how big the nares is, and that's probably why I picked the picture without paying too close of attention. The Carniosauria, elaborate skull sinuses, found in the Middle Jurassic to Upper Cretaceous. And these are the big groups they included: Allosaur, Carcharodontosaurus, and Giganotosaurus. Big, big animals. Probably just as bad as T-Rex was. Allosaur, and this is a much better picture. You can see, look at the eye, it's kind of angled. It's not perfectly circular. We'll come back to that later. Very large nares, and then here's that additional fenestra in the skull. All right, so you're going to start to see this, and here's an Allosaur compared to a T-Rex. Why are we going to see all these openings in the skull? They don't really know, but any good guesses? I keep neglecting this side of the room, but you all can answer too.
Reduce the weight.
Exactly. Reduce the weight. We're seeing hollowing in the rest of the body. These are big heads they're carrying around. Reduce some of that stress on the neck. A lot of the openings were to make room for muscle attachment, and they figured that out. But some of them they can't figure out, like this little additional fenestra. Also, not a lot of people know this. If you look at the models of an Allosaur versus a Tyrannosaur, Tyrannosaur had a really impressive bite force, more so than the Allosaur. Look how wide it can get its jaw. Lots of flexibility. So they probably really grasped onto the animal. The occipital condyle moved quite well with the first vertebra in the spinal column, so they had a lot of flexibility in the heads. So once again, they probably grabbed on, lots of flexibility, tear, slash, and tear technique. Instead of just holding on and crushing. It's probably go in, take a bite, out, go back, take a bite out, instead of just bite and hold on, like some people would assume a T-Rex did. All right, Carcharodontosaurus, big animal. So we'll break the mold on T-Rex. A lot of people think this was bigger than T-Rex, 43.5 total feet in length versus 39.4. This is what's been found of the skeleton so far, and about 33,000 pounds. So not only was it larger in length, but it was also really, really heavy. Giganotosaurus was also larger than T-Rex. Here's what's been found of it, but it wasn't as robust. It wasn't as heavy. So that's kind of debate on what's the largest theropod. And the Spinosaurus was also really, really big. All right, moving on to more of the Coelophysis. So now we're going to look at these groups here. So still on that same clade. So it includes a number of feather forms. So they have found feathers. Well, with the fossils, they found feather imprints associated. They were probably more bird-like than anything that we've discussed so far. And now we're going to see a key difference, a large circular orbit. Remember the allosaur? Had kind of the angled, weird-looking orbit. Now we're seeing a circular orbit and tibia longer than femur. Look at the femur, pretty short compared to the big tibia. Built for speed. When you have a short femur and the lower shaft is longer, that's usually a sign of being fast. Here's another example. Here's a dromaeosaur, really round orbit, and once again, the allosaur picture is showing you the difference. But both are going to have this additional fenestra up front. All right, first we're going to look at the Compsognathus group. That was also famous in Dinosaur, Jurassic Park, the little ones that jumped all over several people throughout the movies. They were considered the most primitive members. Once again, when you see that term primitive, it usually means they were just found further down. Small animals, pronagrade, so they had a horizontal walking posture, kind of like the raptors. Bipedal and carnivorous, they were so small, and you look at their teeth, they were really small. They may have been insectivores, just a guess. Best known examples would be Compsognathus and Sinosauropteryx. So here's Sinosauropteryx, first dinosaur found with feathers, and you can see the feathers on the back and then on the tail. I'm not sure. I didn't look at the original paper to see why they did an A and a B, but I just wanted to show an illustration of where the feathers were found and a representation of what the dinosaur probably looked like. All right, moving on down, tyrannosaurs and ornithomimosaurs. So still in Coelophysis. So tyrannosaurs, it wasn't just T-Rex, there were others, but they were all pretty big, extremely large, with big D-shaped teeth, right? Big conical teeth, kind of like a supersized crocodile. Only had 2 fingers and a reduced forelimb. Look at this though. Remember earlier, we saw several dinosaurs with reduced forelimbs but big pectoral girdles. T-Rex also had a reduced pectoral girdle, but T-Rex also had a head that was pretty much bigger than anything, proportionally. When you have all that head weight out front, you have to reduce weight somewhere. So that's one hypothesis for why the arms and pectoral girdle were so small, is to offset the weight of the head. Well-developed pubic boot. So pubic boot, sorry Mackenzie, I'm getting her head down here. Why do you think that was so large? That's where the center of gravity is, right? So they think they put a lot of the weight was supported by that enlarged pubic boot. So with the ornithomimids, we see a middle metatarsal that's narrow and wedge-shaped proximally. What does that mean? So if you find this, you know the difference between a T-Rex and a duckbill. So we find metatarsals all the time, but we can identify Tyrannosaur when we see this wedge-shaped middle metatarsal. So if you find one of those, you better tell somebody, because that's pretty cool. And as we mentioned, here's some other dinosaurs that we've looked at. Tyrannosaur skulls are extremely robust in comparison, more so than the other theropods seen around the world. And who went to Pete's Museum? Everyone here for that trip? Remember seeing all the skulls? And you go look at the other dinosaurs on the wall, and there was nothing compared to the T-Rex skulls. Once again, look at that. T-Rex skull compared to some other dinosaurs. Look how wide that is. So really, just the main hypothesis based on the skull shape and the teeth is that he grabbed on and just crushed. And then the most famous T-Rex would be Sue, found by the Larson group. And we saw Stan, which is second to Sue in size, I believe. And it's the most complete, most mature, largest T-Rex ever found. And correct me if I'm wrong, but it's in the Chicago Museum?
Yes, it is.
Yep.
Yeah.
Field Museum. All right, moving on to Ornithomimosauria. These kind of look like big ostriches or emus. Very bird-like, long tails, slender build, long arms, with great development in the fingers, probably for grabbing. Characteristics, large orbit, so probably had big eyes, no upper teeth, narrow, long snout, long forelimbs, and flat claws on the pes, which is kind of unique. So if you look at the front claws, they're flattened instead of sharp. So they were probably used for grabbing things, but not necessarily ripping something apart. So some of the major representatives in this group, Garuda Mimidae, the Ornithomimosaurs, and Dinotheres. All right, so looking at the Ornithomimosaurs, they were toothless, found in the Upper Cretaceous. Struthiomimus is a famous one, Gallimimus is another one. This is a really cool one. I get excited about this one. All right, another Ornithomimosaur, probably the largest of the group, and some people are talking about dividing it and putting it in a different group, but when it was originally found, all they found were the arms. Look at those. Those things are crazy. They also have 3 fingers, which is a little different than usual. But that's all they found for 50 years. And now they've found a lot of the skeleton. You can see just how much of the skeleton they've found. But look at that animal. Put it together. That thing is crazy. And if you look at the shape of the skull, really flat, duckbill-like. Look at the feet, look at the arms. They don't really know what this thing did. They think it was, semi-aquatic, probably used that flat beak to sift through plant matter, through the mud. Well, why have those big arms? It doesn't look like it's going to grab anything and bite it in half. Maybe for pulling down plant matter, or scraping through the mud. So you really have to tell a story and get creative with paleontology, which makes it fun. Alvarez-sauridae, this is a weird one. Found in the Upper Cretaceous, only one functional finger. We just keep seeing a reduction in limbs. And I don't use that in an evolutionary way. Sorry, I just mean less limbs. So they might be relatives of the Ornithomimosaurs, but they're not completely sure where they fall out. But for right now, we put them in this group, and that's the unique characteristic, is that one functional finger. All right. So this gets a little tricky, this grouping here. I'm getting to Eumaniraptora or Maniraptora, getting closer to the bird group, and I'll explain. So these are smaller theropods, very similar to birds and some characteristics, found in the Jurassic through the Cretaceous. And here's some of the characteristics. Hands are adapted for extreme mobility. Now this is, I give both sides when I teach, even at my school, but they think it's rotary ability of the hand. So some scientists say, well, maybe that was pre-adaptive for a wing beat, having that extra movement. And what made it so that it could move? Well, it's this semilunic carpal. So it's a half-moon-shaped bone in the wrist. And that is what's key, that extra bone, to the potential movements of the hand. So they had extra flexibility. Now we also see fused clavicles. We also call fused clavicles a furcula. They're finding more and more furcula and other theropods, but for the most part, it's just this group. So that's another characteristic that birds have. And here's an example, semilunate wrist bone. You can see just that extra bone allows a little more flexibility. And here would be both clavicles fused into one and this whole piece together. Well, this is 3 different animals, but both clavicles fused here, the whole thing would be a furcula. Do you know what the function of a furcula is, at least in birds? It's to reinforce the chest area for the force of wings beating. So this is more evidence that evolutionists use for the evolution of birds from dinosaurs is the presence of this furcula. Why have it if you don't have wings? But some of these animals actually did, and some of them glided, so we'll get to that. So here's what we're going to do in my lecture. As you look at different books and different resources, these groups get put together in different schematic schemes, but here's the 5 we're going to look at under Eumannaraptora. The Rhizosauria, Oviraptorauria, Dromaeosauridae, Troodons, and the birds, aves, all right? Other schemes, including your book, put the Oviraptors and the Therizinosaurs under Coelosauria, all right, as a group called Maniraptor. So just be familiar with that as you're studying your book. You may see these listed as Maniraptor underneath Coelosauria. Right? So these were first considered relative of prosauropods, ornithischians, ornithomimosaurs. They weren't really sure what to do with the animal. Now they're considered to be close relatives of oviraptors. It doesn't really matter to me because they're cool. Look at that. Another really weird animal. That's the hand. Look at that. It's a massive, like, sickle-shaped claws they had. So you look at the animal, the rest of the skeleton that they have. Really weird. So they think they were probably similar to sloths in the way they function in the environment. This is not great, even though it looks really cool. It's not really that great for taking down prey. When it's that big, it's probably fragile. But what could it be used for? Yeah, pulling down trees. You look at sloths. Sloths also have really long claws. Theirs are hooked more for climbing, but also for pulling down branches. So maybe for pulling down those high branches with the best foliage on them for feeding. The oviraptors. We found these here last year, right? And well, actually I think someone found it before, but we realized that we had them. And Triceratops is working on this right now. I think they found a couple of bones this year. But they're usually considered Maniraptorans. They were toothless, and basically they called it the chicken from hell. Look at the animal. It's one of the craziest looking dinosaurs you'll see. You can't make this up. Once again, they have that boxy skull that looks quite powerful, but not great for slicing flesh, probably for crushing things. All right, moving on to the dromaeosaurs. These are also considered the raptor group, found throughout the Cretaceous, made famous, or the thing that sticks out about them are those sickle-like claws on the foot that had the ability to move back and forth. Whether it was for subduing prey, climbing trees, or both, we're not quite sure. They come in all sizes. Velociraptor is actually one of the smaller ones, even though it's portrayed as a quite large dinosaur in the movies. But really the larger ones were Deinonychus and the Utah raptor. The Utah raptor was definitely larger than the Velociraptor, but we really don't have much of the skeletons. We only know this animal from most of the lower limbs and some of the upper limbs, but you can do the calculations and the proportions and figure out approximately how large it was. Dromaeosaurs likely had feathers. More and more they're finding fossils with feathers. All right, so you see more and more illustrations of these dinosaurs with feathers. And that doesn't mean they were a bird. Feathers are just a great way to preserve heat, right? They're a great method for thermal regulation. All right, so one of the animals that was found with feathers, Spinosaurus, feathers on the skull, you can see them here, and even feathers on the tail. Troodons, we definitely find these here, late Cretaceous in North America and Asia. Complex pneumatic sinuses, so lots of hollowing of their skeletal systems. Small bodies with really big brains. So quick, agile, and smart. There's another picture, I think I showed it earlier, of what they probably looked like. So when you're digging, be really careful. Their teeth are really small, but you can find these. All right, any questions so far? So we pretty much, in about an hour, ran through the dinosaurs. Yes?
I noticed when we were at the museum and some of the pictures of the bones for theropods, and a lot of the joints, they have like these indentions. Is that specific to theropods, or is that found in other dinosaurs?
I'm not going to say it's specific to theropods, but it's definitely common in theropods. And that's just another example of reducing weight. And you're talking about the indentions on the side, not the indentions in the articular surface, right? Yeah, just another way to reduce weight. And all right, so now we're going to talk a little bit about bird evolution. Birds can fly, bats can fly. Did bats evolve directly from birds or birds from bats? No. And even if you believe in evolution, that's not true. So having feathers doesn't mean you're a bird. All right, having hollow bones doesn't mean you're a bird. These things can be adaptive even when you're a dinosaur. Right? Being fast, light and fast is a good thing, no matter if you're flying or running. But birds in general, if you don't know, are vertebrates, tetrapods with 4 limbs, amniotes, have eggs, and endotherms. Just to give you an overview. Look at the bird real fast. A lot of cervical vertebrae, very mobile necks. Look at the arms. Do you see the general bones that you see in other animals like mammals and dinosaurs? No, you see lots of fusion. If you look at the sacral area, lots of fusion, synsacrum, pygostyle. All the caudal vertebrae are basically fused into this little bone for feather attachment. So keep that in mind as we go through the birds. Excuse me. So we're going to go through some of the animals that were found and kind of talk about evolution and the way they've laid it out. Archaeopteryx, old wing, found in the Upper Jurassic, discovered in 1861. Discovered first feather in 1861. I'm not sure why I put origin of species in there, but if I remember right, it reinforced what Darwin was saying. He published his book in 1859. This animal was found in 1861. So right away, bam, the missing link, right? It looks like a dinosaur with feathers. He's right. So that's why it got famous very quickly. So it has feathers. Okay, that's on the bird side. Antorbital fenestra, that's on the dinosaur side. Partially pneumatic bones on the bird side, which really the dinosaurs have too, so it must be the missing link. All right, so here are the two skeletons laid out next to each other. Here's a present-day duck, Archaeopteryx. What do we see here? What does Archaeopteryx have? Fingers and claws. What does the bird have? Carpometacarpus. It's a fusion of all the hand bones and wrist bones, right? Once again, flight is very stressful on the body. It's a very strenuous process. So fuse those bones to add rigidity and strength, also feather attachment. So these are very different. All right, no synsacrum, no real fusion here. Here we have a synsacrum. The ilium and all the sacral vertebrae are fused into one thing. Very short tail with a pygostyle. What do we have here? Very long tail. No teeth, teeth. So these animals are very different. At first they said it was a bird, dinosaur link. Now it's generally accepted that this is a dinosaur. Rhinovis, the menace from the clouds bird. Really cool. Late Cretaceous. Pneumatic vertebrae, so hollow. Now we're going to see a synsacrum. Okay, all right. That's similar to birds, right? Fibula does not reach ankle. So we look at the tibiotarsus and the tarsometatarsus in birds. If we go back, we're going to see lots of fusion of the bones in this area. Archaeopteryx didn't have that, but now we're going to start to see the fibula reduced and kind of being fused with the tibia. All right, moving on. So I'm trying to paint a snapshot of what evolutionary studies look like. Confuciusornis, Lower Cretaceous. What do we have now? Pygostyle. All right, we also have long fingers and claws, something that looks like a synsacrum, Teeth absent. So now we have an animal with a pygostyle and no teeth. More so like a bird. Enantiornithes, bird group from the Cretaceous. All right, now it gets interesting. Possess teeth. If you look at the hands, they're shortened. It looks more like a carpometacarpus. And we have a claw. So there's still a claw, but we have reduced hands. Otherwise, they look a lot like modern birds. Okay? So keep track of these. So once again, we have what looks like a carpometacarpus, but it has a claw, which means it's not a bird, and it has teeth. Theropods, a seagull-like Upper Cretaceous bird found in Kansas with some of the mosasaurs. Look at this animal. Pygostyle, synsacrum, fusion of the leg bones, carpometacarpus. What's different from birds though? Teeth. Yes?
There are many of these skeletons that are having missing parts in the skeleton. So how, with those missing jaws and bones, how do they reconstruct the bird in the most accurate way?
They do the best they can. Like if they don't find teeth, they're not going to put teeth in. So when I say these animals have teeth, they likely did. And these animals, most of these are pretty complete. If you're looking at other Archaeopteryx, some of these fossils, this is a lot of time the way they find them. So these skeletons are usually complete and they make national headlines. So I wasn't there, but they really try to do the best they can. All right, this is where it gets cool. This happened in 2015, a year before I came on the dig. This Archaeornithera was found in the lower Cretaceous. That's kind of weird. This animal is a bird. All right, this is a bird. This is a true bird. This pushed bird evolution back 5 million years. So this bird is older than Confuciusornis. Boom, that's weird, right? Push it back 5 million years. Let's put this in perspective. This would have evolved in 10 million years after Archaeopteryx. So we're talking about millions of years on the evolutionary timeline to go from this to a modern bird. So we're going through all these steps over long periods of time. They found this in 2015. This thing would appear 10 million years after Archaeopteryx, and it would have predated this guy. So as evolution's happening, so let's look at the timeline. This is, a typical timeline published. As it's happening, and I didn't mention all these animals, but they're in your book, we're getting to modern birds up here. And I understand evolution quite well, and they don't always put it in a linear fashion, but here they did. Instead, it kind of branched out just like this. So this threw a kink into things. This really messed with evolutionary timelines because this bird was already around right here. So the time that it took to go from here to the modern bird, that wasn't true. The bird was already present here in its modern form. All right, evolution solved that by just saying that maybe there were two different branches that evolved. Maybe there was a branch that evolved from Archaeopteryx, this branch, and another branch that evolved from Archaeornithera. So all they did was adjust the timeline and add another branch. Okay? So I'm not going to tell you yay or nay, but when we look at these things, all I want you to see is these traits are advantageous to the animal and its environment. It doesn't mean Archaeopteryx is a bird. It was a dinosaur. It doesn't mean this was a bird. But this is a bird. And this was around right here. So the bird evolution theory from Theropods is one of evolution's strongest points. And it was hard to explain, but in 2015 things changed. So, they're coming up with their hypotheses, we have ours, but I just wanted to make you aware of this because it was a really interesting find.
Something that has me wondering is, why did they pick theropods, the creatures with the lizard hips, instead of the dinosaurs with the bird hips?
Jonathan, were you hollow bones, the same skeletal designs? So even after this, like the lizard hips, they're gone by this point, right? So they picked theropods because they were the animals with hollow bones. And like I said, with that semilunate bone right here, I don't know how far back I have to go, but anyways, the one that gave the wrist more flexibility. So they really saw the steps. It was really working in their favor quite easily. They weren't even having to stretch the truth to do it. So, and there still is a lot of evidence that works in their favor for this, but it was a great find in 2015 to say that birds were already around before these other animals ever appeared in the fossil record. But yeah, to answer your question, all the things we talked about today are why they threw birds as the next link in the process, because if you look at all the other animals, they just don't match up.